Well, good morning. Welcome to the last week. We're just going to work on chapter 14, not quite the whole chapter. It's a very dense chapter, a lot of stuff on waves, sort of something that a lot of textbooks take 2 or 3 chapters to do. They do it all in one in Wolfson. So we're just going to do up until before the Doppler shift stuff, and just to the level, sort of light touch level. So I want to talk about these, again, course evaluations. So you did it. Yay. Yeah. Congratulations. So every student will get 1% boost added to your mark. But you can still keep on evaluating for another 3 days.
We're going to call you Oprah now. Give everybody 1%.
It's a bumper. The other thing I wanted to do actually is, if I go and show this video, this is about resonance. Can I send it to all? This is my daughter, Zainab Harlow. I filmed this maybe about 6 months ago when she was 5 years old. She's 6 now. And she's discovering resonance. So let's see what she does. First thing she does, she just tries to use her legs at the wrong frequency. No, no, no. You have to match the natural frequency of the swing, Zainab. Come on. That's the wrong frequency. Okay. She's sorting it out. She's getting herself adjusted. There we go. Okay, now, the frequency that she's moving her legs at matches the natural resonance frequency of the swing, and so she's increasing her amplitude. And that is resonance. So she's managed to discover that. This is a little bit of prompting. I think she just basically figured this out by herself, but she was humoring me at the beginning because I was saying, for the purpose of the demonstration, try to shake yourself at the wrong frequency. So, and a student asked me, and I think it's a great question, where does the external force, the external net torque come from? So there's only 2 main forces that are on the child on the swing, which is gravity and then the tension from the chain in the swing. I guess there's also air resistance, but I don't think it's air resistance. You only need a little force, but I think it's probably initially coming from actually the tension in the chain. She's moving her body around so that the direction of the force line of that tension is not directly through the pivot point, I think. And then eventually gravity takes over as being the main external torque. So it's amazing actually that the human body can figure this stuff out and solve the problem, solve the physics problem, even if you don't totally understand where the torques are coming from. I don't know why I keep going back to these Kill Bill references, but this is when the bride was talking about something about her fiance, just before the fiance gets murdered, by the way, but saying that he works at a music store, he loves music, and Bill says, or he's fond of music, and Bill says, aren't we all? So I will be teaching a course called The Physics of Music starting in January. It's an online course, so I've been recording videos for that, thinking about that a lot. And another music lover is your practicals coordinator, Dr. Seelfin. I don't know if you remember her. She introduced herself in the first lecture, but she's been behind the scenes of your practicals, training up your TAs each week. And she has some friends who are in a choir, and there is a way that you can sing. You can stand on the stage here and get the whole con hall to match kind of a resonance of the overtones of what you're singing. And so we're going to bring a microphone, a fast Fourier transform, and try to see if we can measure those frequencies as they're singing. It's should be about a 10-minute sort of musical demonstration on Wednesday morning. Some stuff from this morning. The exam proctor said, "Take off your jacket." And I replied, "Man's not hot, never hot." So I guess to me, I actually have you guys to thank for the fact that I even get that joke, but please, this is kind of like, I don't know, making a joke about a bomb when you're in the lineup for security at an airport. You just don't do it, okay? And the invigilators for a final exam are not the same as the invigilators for a midterm. The midterm is run by the physics department, by us. The exams are run by the examination office, which is based out of Sid Smith. And they hire these people, they're kind of like cops in a way. They're there to oversee the exam, and they're pretty serious, some of them, and so I wouldn't joke around anyway. Some of them are perfectly normal people. In the wave part about wave intensity, you brought up the formula, intensity is power divided by area. But from reading the text, I now know, okay, I know it's power per unit area, but how does it relate to the amplitude? And this is a great question. So you have the amplitude of a wave. If a wave's going along, it can have a small amplitude or it can have a large amplitude, right? Where this is the middle. This amplitude A does relate to the intensity, but I'm not really telling you how. Because first of all, it's sort of complicated, and second of all, it is different for different waves. It relates differently for an electromagnetic wave or for a wave on a string or for an ocean wave. But in each case, as the amplitude increases, this intensity, power per area, also increases. And normally the intensity increases as the square of the amplitude. But that's all you have to know. It's sort of beyond this course. In chemistry, we learned that frequency of a wave is equal to the speed of light over the wavelength if the wave was in a vacuum. If we have a problem with a wave in a vacuum, can we use this equation? Well, kind of. So, yeah, this is the equation that I like to use, is that the speed of the wave is equal to the wavelength times the frequency. You can also solve that out for the frequency is the speed divided by the wavelength, so that's okay. I guess probably what you learned in chemistry is about an electromagnetic wave in a vacuum, so that's fine. But for any wave, this is true. If you've got a frequency and a wavelength, you multiply them, you get the speed of the wave. What does held taut mean? Yeah, so taut means not slack. So if you have a string or something, or a cable, you pull it. If it's a straight line, so there's sort of a tension through it, then it's taut. We'll talk about that a little bit more. Let's do Learning Catalytics. The constant K, introduced in this chapter, in your reading, is it A, the Boltzmann's constant, units joules per Kelvin, B, the Coulomb constant, units Newton meter squared per, well, it should be capital C squared, Coulomb squared, C, the spring constant with units Newton per meter, or D, the wave number with units radians per meter. You select from that list. Yeah, so I believe that this lowercase k might be the most overused letter in all of physics. But so in different chapters of Wolfson, all of the above are correct. Kind of funny. But anyway, in chapter 14, it's this last one, wave number. It's kind of like a frequency, but it's like a spatial frequency or something. Correct. And the way it relates, so remember that omega was equal to 2 pi over the period, so that's like the time frequency in angles. Well, this k is equal to 2 pi divided by the wavelength. It's like a space kind of frequency. So t being the period, how much time it takes for the wave to repeat. Lambda being like a distance, how far does the wave go before it repeats. So this is waves, and I did last time ask you, 2 of the 5 senses depend on waves in order to work. The answer, which of the 2, is sight and sound. Sound is a pressure wave which travels through air. So these are sort of an exaggerated diagram of little air particles. They are more dense, less dense, more dense, less dense. So the density of air in a sound wave is what's varying. The density for a pressurized gas is proportional to the pressure of that gas. So the pressure is also varying. And this is normally what we measure, is we measure pressure versus distance. Although it sort of seems to be exactly the opposite in this graph. It seems like the graph is pressure increasing downwards. And then light is an electromagnetic wave. What that means is that there's an electric field, which is represented by these red lines, and the magnetic field, which is represented by the blue lines. What does that mean? Well, if there was a particle at, for example, this point, and it had a charge, a positive charge, it would feel a force upwards. Or if there was a little compass sitting here, then the north would point sort of out of the page there. So there's two ways of measuring electric field or magnetic field, is with a charged particle or with a compass. And if an electromagnetic wave goes by, then a charged particle is oscillated up and down, and a compass will feel the magnetic force going back and forth. So a vibration from like chapter 13 stuff is a periodic motion back and forth of a particle around an equilibrium position, like that child in the swing. But when many particles that are neighbors to each other are oscillating, you can get a wave traveling through some medium. Example would be water waves. That's sort of what we normally think of, light and sound. And some links to some animations of this stuff which don't show up very well on a doc can. But two of the numbers that come out from when you look at a wave like this, amplitude, we normally call it A, is the distance from the midpoint to the crest or to the trough. And what's interesting is that amplitude was, back in chapter 13, used for simple harmonic motion, even though there was only one object moving back and forth. And so there was this sort of example of if you have a mass on a spring going up and down and you track what its position is versus distance by, I guess, if it was spilling sand onto a conveyor belt and the conveyor belt was moving towards the right, you would get a wave pattern. And there'd be an amplitude and there'd be a wavelength. Wavelength being the distance from the top of one crest to the top of the next, or the distance between any successive identical points on the wave. It's like a spatial period. And then the wave speed, we already talked about this, describes how fast a disturbance moves through the medium. It's related to frequency and wavelength. So again, I like to call it wave speed is equal to F times lambda. So this is the Greek letter lambda. Looks like that. So example is that if this bird was watching the water go up and down on the pier or post where they're sitting on, the bird could see a frequency just by looking at the water directly below her, I guess. And then if you also somehow just looked at a snapshot, a picture of the wave, and you could measure the distance between two successive crests of the wave, you could multiply those and get what the frequency you can measure in one place, and then the wavelength, and you can find the speed of the waves as they move along. And then there's a couple of different kinds of waves. There's transverse waves, where the medium vibrates perpendicularly to the direction of energy transfer. This is what we normally sort of think of. And then, we didn't bring the big rubber hose, did we? Okay. So where the little particles oscillate back and forth one way, but the direction of energy transport is side to side. So I guess we can actually show this wave machine that kind of does it. This is an example, somebody asked if they could play with this, of a transverse wave. So you can kind of see what's oscillating are the little particles, maybe at the end here, these little dots. It looks kind of cool and it's very hard to balance it. But it's just a lot of sticks, and they're all connected by a torsion wire in the middle. So if I start a disturbance in one end, it travels along. And it actually reflects and comes back, whoop, and rotates the whole thing. And I could maybe try to get a sinusoidal wave going by going like that. Whoop. Again, tilts it. But you've got the basic idea. If you look at any particular particle, it just moves up and down. It oscillates up and down as the wave travels by. So there's two things going on. There's the disturbance, which is moving from one side to the other, sideways. And then there's the individual particles, which are moving just up and down. And that's a transverse wave. Can we go back to the dot cam? And the speed of transverse waves on a stretched string, didn't really derive this, but we're just telling you, is equal to the square root of the tension in the string divided by mu, where mu here, again a reused letter, I think this used to be coefficient of friction, but now it's the linear density, the mass per unit length of the string. And so, next learning catalytics question is two wave pulses travel along the same stretched string, which is true. We've got speed of A is a low amplitude pulse, and speed of B is a higher amplitude pulse. So is the speed of A greater than the speed of B, or is the speed B greater than the speed of A? Or are they equal, or not enough information? Give me a minute to chat about that. Okay, well, I guess what I was trying to get at here was that the amplitude shouldn't depend much on the speed. Or sorry, the speed should not depend on the amplitude. The wave speed depends on the properties of the medium. So hopefully you got it, but it was sort of similar to this one from this morning. You're generating traveling waves on a stretched string. If you suddenly wiggle more rapidly without affecting the tension, so this is where you increase the frequency of the waves, they should go the same speed as well. So in both cases, what's happening is you've got, it sort of looks like this. F over mu. F equals the tension in the string. So that could change if you stretch it more. And maybe if you put a higher amplitude pulse, you might think that that might actually somehow increase the average tension. So that would be correct, I guess. And then mu is the density of the string. Density of the string. It's in kilograms per meter. So a different string, a thicker string will have slower waves. So if you have a thicker string in your guitar, for example, the waves propagate slower on it back and forth, and so you get a lower frequency. You have a question? Yeah.
V is equal to frequency times lambda. Aren't you wiggling more?
Yeah, so also V is equal to frequency times lambda. So yeah, if the wavelength was the same, then if you increase the frequency, you'll get a faster speed. But what would happen here is that the speed is the same because it's fixed by this, so just the wavelength would decrease. Okay. So lambda is not fixed. I guess you would say if you were generating traveling waves and you increase the frequency but somehow keep the wavelength the same, then you'd have a higher speed. But the only way you could do that, I guess, is to change either the tension or the mass density in the string to compensate. That's a good question. Let's keep going here. Another learning catalytics question. And this one maybe is more mathy. You can actually do it. Give me a minute. Showing results. Yeah, so this is kind of one of these ratio things. You have, again, the speed is equal to the square root of the string tension, which we call F. I keep wanting to put T. I think the reason we don't use T in this chapter is because it could get really confusing. You could confuse it with the period T. So F for the tension in newtons divided by this string density in kilograms per meter. So if you increase F by a factor of 4, square root of 4 is 2, you'll increase the speed by a factor of 2. And this morning you had this pre-class quiz, waves travel along a 100-meter length of string, which has a mass of 55 grams and is held taut with a tension of 75 newtons. So you can do it by separating it out. Mass over length is 55. I want to convert that to SI units, so I have to go 10 to the minus 3 kilograms divided by 100 meters. That's the mass density of that string, which is going to be 5.5 times 10 to the minus 4 kilograms per meter. And then if you say V is equal to square root of the tension divided by mu, tension was 75 divided by 5.5 times 10 to the minus 4. I got 369.3 on my calculator. So the V is about 370 meters per second. So again, this whole chapter is sort of a light touch. We're not getting very in depth into where this equation comes from, but we are applying it and using it. Here's another application. Does this show up? Yeah, that's true. So maybe 400, even better. Yeah, I'm really bad at significant digits. I don't care about them, but that much. But anyway, so 400, even better. Because there was one significant digit in the 100-meter length. That's a good point. I personally would give 100% for either of these answers. I'm just not that picky, but sig figs. Okay, 80-kilogram climber. We better be careful here because that's one sig fig. Okay. Hangs from a rope 20 meters below a rocky overhang. It's a little hard to picture that. So here's the rocky overhang, and here's the rope, which is sort of hanging down, I guess. And then there's the person. That's my beautiful diagram. And there's 20 meters. This person at the bottom is the 80 kilograms. 80 kg. And then they just tell you the linear density of the rope. Mu is equal to 37 g per meter. So again, that's not in SI units. So I'd say maybe 37 times 10 to the minus 3 kilograms per meter. I would write that down right away so I don't get caught by that. And then it's asking approximately how long would it take a transverse pulse to travel the length of the rope from the climber to the overhang. So maybe I could imagine you might want to send a signal. I don't know, send me down a bottle of water or pull me back up. So you like send pulses up the string to whoever's, I don't know, dangling you from up there. Anyway, so there's a little pulse, and it goes upwards. And the question is, how long does it take? So you just need to find the speed of the waves. So find the speed of the wave. And then if it's constant speed, which hopefully we can assume, then you can just use that the distance is equal to v times t, something like that. So I guess if you do the free body diagram of the climber, then you have the force of gravity of the earth on the climber acting down. You got the tension acting upwards. This is the tension. Well then, this tension is equal to mg, where that's the climber. So v is equal to square root of f over mu. I've got square root of mg divided by mu, square root of, I'm going to use the 80 kilograms times 9.8, and then divide it by our number 37 times 10 to the minus 3. So I've used SI units in all these three numbers, so I should get a SI unit meters per second. I got 145.6. I'm not going to round because I'm in the middle of a calculation, so that should be enough. And then let's use this, and we're asked to find the time. So we'll do t is equal to d over v is equal to 20 meters, the distance it has to go, divided by the 145.6. So I got 0.14 seconds, which I guess it seems a little bad, but I guess I could round it to 0.1 seconds. And then I want to note something that I did here. I assumed constant speed, so I want to note that we neglected, somehow bizarrely, the mass of the rope. In calculating the tension. Because what I did is I just thought about, okay, what's the tension in the rope way down at the bottom of the rope where the climber is hanging? And I thought about the free body diagram of the climber. Well, there's gravity pulling down, tension pulling up. So I think that this is correct for calculating the tension at the bottom of the rope. But if you think at the very top of the rope, you're suspending not just the person at the bottom, but also the whole rope. So I think the tension at the top of the rope should be a little greater. So I guess you could get the tension at the top of the rope supports, am I still on the screen there? 80 kilograms plus maybe, I don't know, 0.037 times 20 meters. That would be the mass per unit length of the rope times 20 meters, the length of the rope. I got 81 kilograms. So I think waves should actually be a little faster at the top of the rope than they are at the bottom of the rope. But since we're only on one significant figure anyways, it's definitely not going to matter. It's like about a 1% kind of effect. But thinking a little more deeply about it, it should be an accelerating wave as it goes up. Okay. So the next kind of wave I want to talk about is longitudinal waves. This is where the medium vibrates parallel to the direction of energy transfer. So the little particles in a transverse wave, their actual motion was up and down, while the wave went from left to right. Well, a longitudinal wave is where the shaking motion back and forth is parallel or anti-parallel to the direction that the energy goes through the medium. So examples of that would be like a sound wave. And what happens is that when these particles are shaking back and forth, the way they oscillate, they create regions of higher density and lower density. So if you were to plot somehow, this is distance versus something like density, and you would see, if you can just see it, it goes a little bit above your average density and then a little below, a little above, a little below. Oop. And that's what you're ending up plotting. You're not actually plotting the motion of the particles, but you're plotting the density of the particles. Okay. So those are the two kinds of waves. Now I want to talk a little bit more about how to graph them. So one way to look at a wave is to imagine looking at the whole wave, but only for a particular instant of time. And this is called a snapshot graph, because you can imagine the wave is traveling along and you take a photograph of it and there's a flash of light because it's too dark or something. And during that flash, you see what the whole wave looks like. So you're plotting some, if it's a transverse wave, delta y versus the x position. So for a pulse, for example, it's literally just a picture of the wave at that particular instant of time. And then if you've got a wave that travels along, then you'll have a different snapshot for every subsequent instant of time. So this is where we're going to get to a history graph. So imagine you've got a pulse going along, and it has a sort of a steep beginning of the pulse, and then a more shallow, less slopey end of the pulse. And it's going towards the right. So I want to think of these 4 different snapshot graphs happening at different times. So this is maybe at exactly 1 o'clock in the afternoon. This is 1 o'clock plus 1 second, 1 o'clock plus 2 seconds, and 1 o'clock plus 3 seconds. So if you measure time as going from beyond 1 o'clock, it's t equals 0, 1, 2, 3 seconds. Well, the y position, the position of the disturbance, starts at a low time as starting up the steep end, and then after more time goes by, it then goes down the lower end. So this is maybe t equals 0, t equals 1, t equals 2, and t equals 3. So if we make a plot of this delta y versus t, we will find out what the history of this particle at x1 is over time, called a history graph. But it ends up being kind of flipped, because remember, for low values of time, you're on the steep edge, and for higher values of time, you're on that less shallow edge. So it ends up being kind of flipped for waves that are traveling from left to right. So time t equals like negative, it's just the pulse isn't there yet. Then at time t equals 0, boom, you start hitting that beginning of that pulse. Then the particle, all these points in this graph are just that particle at x1. It goes up, and then it goes down. So this is not a snapshot of the wave. It's not what the wave really looks like. It is plotting the history of the particle which sits at position x1. It takes a little bit of... Basically, the problem with these waves is that they are a function not just of time, but also of position. So you've got y, which is your disturbance, or delta y as it's called here, and you've got x, and you've got t. So it's three variables to keep track of. It's sort of a 3D problem. So we can't draw things in 3D, so we can either draw y versus t or y versus x. And just sort of think about it one way or the other. And then we have sinusoidal waves. And again, this is in the pre-class video or the reading, but your y here, delta y, is equal to a times cosine of, instead of omega t, we have kx minus omega t or kx plus omega t. It's very similar math to what we were doing with oscillations. You're using this button on your calculator, cosine or sine, as being a function, which is converting something, which has to be in radians, into like a position. So whatever is in here is the argument now. It used to be omega t. Well, now it's some function of x and t. And you've got an omega, which is angular frequency, 2 pi over t. And now you've got this new number we talked about today, your wave number. And actually, there's a new equation. This is very similar if you've got, V is equal to F times lambda. Remember that? Well, the frequency is equal to, omega is equal to 2 pi F. So that frequency is equal to omega over 2 pi. And also, the lambda is equal to 2 pi over k, if you flip that equation around. So we know that speed is frequency times wavelength. It's omega over 2 pi times 2 pi over k. So the 2 pi's cancel, and you get that if it's frequency times wavelength, it's also omega divided by k. And that's where that equation comes from. It's the exact same equation. So it's a little hard to picture, but this is back to transverse waves. This is a snapshot graph of a wave that's going from left to right. So this arrow up here is telling you the direction of the pattern. So this pattern, which looks like a sine wave, is moving towards the right. But what's happening is that the particles themselves are just either moving up or down. They're oscillating with simple harmonic motion as this wave travels by. So, at the top and bottom of the motion, the particles are stopped. That's when they reach their maximum or minimum position, so they're turning around. But look at this particle right here. The wave pattern is moving from left to right, so in a couple seconds, what's going to happen is this particle is going to have to go up here in order to be on the crest part of this sine wave as the pattern goes from left to right. So this particle is moving up. This particle over here, it's also at its equilibrium right now, but the pattern is about to move from left to right, so it's going to have to go on the trough part, so it's going to have to be going down. And so the positions of any particular particle and the velocities are given by these equations. Let's see if you're sort of following it. This is one where you have to somehow draw a little vector on your Learning Catalytics. So, a wave on a string is traveling to the right. So this is the, wave direction. So this whole pattern of a sine wave is moving from left to right. at this instant, the piece of string marked with the dot at its equilibrium position is definitely moving. What direction is that piece of string moving? And try to draw it with your finger or your mouse. I'll give you a minute. So I think actually 79% of these did come in right. But the particles themselves are moving either up or down. Okay, they're exhibiting simple harmonic motion, and this is a transverse wave, so they're going up or down, as the pattern moves from left to right. So it's either up or down. And then what I tend to think of is, okay, this pattern a little later will be like this. So this is later. So in order for this particle to get where it's going to be a little later, I think it has to be moving up, because it's going to be up here. Make sense? That's how I chose between up or down. So I think it's up. Up. Down was a good guess, but I think it has to be up. Okay. So there is some stuff that I wanted to talk about wave intensity, but there's no cool demo to go with it, so I think I'm going to skip it and talk about it on Wednesday. What I do want to talk about is sound waves. So once again, if you've got, we've been talking a lot about transverse waves, but if you have a longitudinal wave, you can plot pressure or density versus distance. So pressure is proportional to density. So as these particles are getting more crowded or less crowded together, you'll have, in the more crowded regions, higher pressure. Less crowded regions, lower pressure. Where the center is atmospheric pressure. So if you have a speaker or some surface that's moving back and forth, then what will happen is that waves will travel outwards from that. That's what a sound wave is. And I asked you this morning, what determines the pitch of a musical note? Well, that's frequency. Can we try to do the demo right now? What I have is a frequency generator here, which Kevin has set up to be at 200 hertz. So I'm going to play a 200 hertz frequency. And what this is, he's got it set to sine wave. So this is a pure tone, a sinusoidal wave. We'll try to hear it. So this one's not going to go over the Con Hall speakers. It's coming from these speakers, so you should. Okay. That's 200. That's 200? Yeah. Okay, so that's 200 hertz. And then you go to 300 hertz, 400 hertz, 500 hertz. Now what's going to happen with this demonstration is that we're rapidly getting into annoying sounds. There was a Dumb and Dumber, I guess, movie where it says, what's the most annoying sound in the world? Well, this is going to be it. So, okay, 600 hertz, 700 hertz. We get up to 1,000 hertz, it sounds like that. The other thing about this is that this is a pure tone, meaning that it's a sinusoidal oscillation. You can also have other tones that are not exactly as sinusoidal, like there's triangle, there's square. Anyway, we're going to keep on sinusoidal. But you can have the same frequency, but with a different shape, and that gives you a different quality of the tone. Let's go up to, there's 2,000 hertz, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. So I got to go back to 10K here. Hold on a second. So there's 10K. So now it's going to get into the range where it starts to get a little hard to hear it. Okay, so that's 15,000. You guys hear it? Okay, good. Okay, I can't hear anything at this point. This is 17,500. Can anybody hear it? You guys, raise your hand if you can hear. I can hear nothing. Okay, I've got 45-year-old eardrums, and I cannot hear this at all. Like, I could turn it off and on. Let's turn it off and on. Like down, off, on. There's no way you can convince me there's any difference. So you have younger eardrums, and so you are more sensitive to higher frequencies. And as your eardrums age, what will happen is that they'll get stiffer, and they won't be sensitive to this kind of thing. Let's go a little higher. Let's try 20,000. Can anybody hear 20,000? Let's be quiet. You can hear it? Off. Listen for a very high pitch. You can hear it? I believe you. Let's try 22,000. I have no idea what's happening, so. Can you hear it? Anyway. Let's turn it off. Somewhere there's a dog who's like freaking out, going, ah, what's happening? Okay, so we did talk a little bit about ultrasound. So your ears are able to detect sinusoidal waves with frequencies between about 20 hertz and 20 kilohertz. So, and for me, it's more like 20 hertz to about, we saw about maybe about 15 kilohertz. But outside this range, if you're below this range, it's called infrasound. Your ears can't detect it. If it's above this range, it's called ultrasound. Again, your ears cannot detect it. And you can use ultrasonic waves to actually map the inside of a human body. You can send the sound waves in there, and the wavelength of the sound is very small, so you can get nice high-resolution images of maybe your baby inside someone's body. So, let me just check the time here. We are running a little bit out of time, so I think what I'm going to do is, again, encourage you to look at the course evaluations. We're going to try to get up to the end of section 14.7 on Wednesday. We might not make it, but we've also got Thursday. I'm going to be in this room from 11:10 to noon, finishing up chapter 14 and doing a bit of course review. And we also talk a little bit about Physics 132. The other thing, as we mentioned, is we've got the singers coming in on Wednesday morning. So please be here for that. Those will be right at the beginning of the lecture. And we'll try to get some overtones in this room. So, see you Wednesday.